Hello and welcome back, Chem 51, to your Week 6 pre-activity lecture. This covers Activity 54A, so please be sure to read that before and after watching this video. So we did speak about classifying reactions in Chapter 5, but I'd like to just organize into a table what we are looking at. So when you have a precipitation reaction, when you physically do this in the lab, you're going to go from clear to cloudy. So you can't see through it. So you're starting out with two clear solutions, forming cloudy suspension. Okay, so what do we need to look for in the equation? If we're presented with an equation and we need to classify it, we would look for the reactants being aqueous. We'd have one solid product. Okay, and one aqueous product. One solid product, one aqueous product. Okay, so what do we look for in an acid-base reaction? Not much, unfortunately. There's possible heat. Not all the time. No visible reaction. Okay, so what are we looking for in the equation? We are looking for liquid water and a salt. Okay, so at this point you would just always look for your telltale products for an acid-base reaction. So now for a redox reaction, there's many different types of redox reactions, as we'll go over in a moment. But one thing you could see is replacement of an element. Okay, so you could start with a copper wire and then end up with the copper being replaced by silver. That can happen. You could also have a gas release. You could have possible heat. Depending, yes, possible heat depending upon the specific reaction. You can also have fire. That's fun. So what you're looking for in the equation would be an element as a reactant or a product. Okay, you can also look at a change in charge. Okay, So that's just a quick way, a quick reference for you to be able to classify a reaction, classify a chemical equation when you're presented with one. One thing I'd like to go into a little more detail about is that you have some different types of redox reactions. Technically, they're all the same. They're all just a change in charge, or sometimes we would say oxidation state. But there's three types that look very different. Okay, so our first type is with two metals. Okay, so you have an aqueous ionic metal. So if you have aqueous silver nitrate, you have aqueous ionic silver. You have silver ions in solution. So your aqueous ionic metal replaces an elemental metal. And then that elemental metal forms ions. So what happens is the elemental metal donates electrons. It donates electrons to the ionic metal. Okay. Well, the second type would be with a metal and an acid. Okay. So an elemental metal will donate electrons to two hydrogen ions, so two protons, forming elemental hydrogen. So a reminder, hydrogen is one of your diatomic elements. So our third type, which looks very different, but we're probably quite familiar with, is combustion. Okay, in which case a hydrocarbon something that's primarily carbon and hydrogen, and as well as elemental oxygen, which is O2, another diatomic, are going to form carbon dioxide and water. Okay, so those are your telltale products for a combustion reaction. So let's just look at a few examples, 5 examples, and we're just going to balance these equations. So using the method that we went over in the lecture. So this first one, I have some potassium iodide. I have some mercury 2 nitrate. I have some mercury 2 iodide. And I have some potassium nitrate. So I'm going to pick my mercury 2 nitrate as my first compound. So that gives me 1 mercury atom and 2 NO3 minus, 2 nitrate ions. And so this is 2 plus and this is minus. So if I have 2 nitrate ions on the reactant side of the equation, and on the product side of the equation in the formula there's only 1 nitrate there, then I have to give this one a 2. So that will give me 2 nitrates and 2 potassiums. Okay, so nitrate is balanced. So if I have 2 potassiums on the product side of the equation here, then I'm going to need 2 potassium iodides, since there's only 1 potassium in there. And so that's going to give me 2... Oh, hang on, my pen doesn't want to work. 2 potassiums, there we go, and 2 iodide ions. Okay, so finally, if I have 2 iodide ions on the reactant side, and I have 2 in the formula, on the product side, I can give that a 1. That gives me 1 mercury 2 plus ion and 2 iodide ions. Okay, and now we're balanced. Okay, and so this was a precipitation reaction, and we can tell from the solid product. Okay, this next one, we're looking at an acid-base reaction. We can tell by the liquid water as part of the product. And so let's try that. So I will give my potassium phosphate a 1 here. That's going to give me 3 potassiums, 3 potassium ions, and 1 phosphate ion. Okay. If I have 1 phosphate ion here on the product side and there's 1 here in the formula on the reactant side, I will give that a 1. And so that's going to give me 3 protons and 1 phosphate. Okay, so I have H plus and OH minus forming H2O. The potassiums are a little easier to deal with. So if I have 3 potassiums on my product side and 1 potassium here on the reactant side, I'm going to have to give that one a 3. So that gives me 3 OH minus and 3 K plus. So I have 3 H plus, 3 protons, and 3 OH minus, which are 3 hydroxide ions. Okay. And so that is giving me 3 H2Os. Okay. All right, moving on. This next one is going to be one type of redox reaction. So this is an elemental metal. We can tell that zinc is elemental. It's solid. It's not bonded to anything. And then we have nitric acid, HNO3. Okay, and then we're going to form zinc nitrate and elemental hydrogen. Okay, so I'm going to start with zinc nitrate, give that a 1. So I'll have 1 zinc 2 plus. And just a reminder, zinc is a transition metal, but it still always forms a 2 plus. It's one of the exceptions. And then we have 2 nitrate ions. Okay. If I have 2 nitrate ions here on the product side, I have to give my nitric acid a 2. And then I have 2 H plus, and then 2 NO3 minus. Okay. So if I have 2 H plus here, notice the charge is going to be different. I would give that a 1, and I'm going to say 2H. I'm not going to say 2H plus anymore. So we have a mass balance, but we don't, between the hydrogens, but we don't have a charge balance. Okay, but let's look at the zinc. If I give zinc a 1, that gives me 1 zinc atom, which is not charged, but then that will form zinc 2 plus, which is charged. So between the 2 species, the zinc and the hydrogen, I have a charge balance on either side of the equation. Okay, so these last 2 are combustion reactions. And so what we need to do is employ a strategy where we save elemental oxygen for last. And that is because it appears in both of the products. So we need to figure out how much of each of those products are before we can get the total number of oxygens. So I'm going to start by giving my hydrocarbon a 1. That gives me 1 carbon and 4 hydrogens. Okay, and so I will use only the carbon and hydrogens to determine my product. So if I have 1 carbon here, I'm going to have 1 carbon there. And 2 oxygens. If I have 4 H's here, I'm going to have to give that a 2. Okay, and then that'll be 2 oxygens. So I need 4 oxygens total. That means that I have to give my O2 a 2, because that's 4 oxygens. Okay, now everything is balanced. Now let's look at a situation that could be a little more complicated, where we end up with an odd number of oxygens on the product side. So let's start out. We'll give our hydrocarbon a 1. That's going to give us 3 carbons. And, oh, I don't know what happened there. 3 carbons. Terribly sorry. 6 hydrogens. Okay. So that's going to mean we need 3 CO2s to match the carbons. 3 carbons, that matches. And then, so that means I have 6 oxygens here. If I have 6 hydrogens here, then I need 3 waters to balance that out. That'll give me 6 hydrogens. And it'll give me 3 oxygens. So I have 9 oxygens total. But this is an O2 molecule here. That's an even number of oxygens. So I have to do something a little bit sneaky. I'm going to say 9 halves. I need 9 halves of an O2 molecule to be able to balance this equation. And that gives me 9 oxygen atoms. Now, can I really do this? No. But I can do it temporarily and then multiply the whole thing by 2. And that will give me 6 waters, 6 carbon dioxides, 9 O2s, and 2 C3H6s. Okay? So it's totally okay to do fractions temporarily if you need to. Okay, this concludes our pre-activity lecture. I hope you got something out of this, and thank you for your attention.